Hello everyone, my name is Gareth Woolcock. I am a gameplay and UI programmer on tanks. Welcome to the second video in our series in which we pull back the curtain a little and show you some of the Unity multiplayer functionality that we used in implementing tanks gameplay. If you've not yet watched the first video in our series, I encourage you to. It goes a little into the history of the project as well as showing off some of the gameplay. Alternately, feel free to download the game and play it yourself. It's available on the Apple App Store, the Google Play Store, and the Windows Store for download right now. Download links are available in the description below this video. You can also download the project itself for import into Unity, so you can dig into it yourself. A link for that is also in the description. And now, without further ado, let's get into Unity multiplayer. Any multiplayer game needs to implement two broad spheres of functionality. The first is session and connection management. In other words, you need to get all of your devices, all of the instances of your game talking to each other. Now, with games, that generally comprises of creating game sessions, broadcasting them, allowing people to browse any sessions that may be active, and allowing them to connect to those sessions. And then once everyone's connected, making sure that all of the traffic is routed towards the correct people in the session. Alright, now once we've got packets flowing in between our players, we also need to know what to do with them. And that's where the second sphere comes in. We need to compile and send the data that we need to synchronize all the different instances of our game in the session. We need to receive data from other instances of the game and distribute it to the scripts and objects that require it. And then we actually need to act on the information. We need to take this information and we need to turn it into gameplay so that it's smooth and responsive and fun for the user. Now, fortunately, Unity Multiplayer Services takes care of both these spheres. Let's take a look at how. Sphere 1 is taken care of by the Unity Multiplayer Services themselves. These you will subscribe to with your Unity account. And they consist of the matchmaking server and the relay server built on top of the infrastructure that allows them to work smoothly. The matchmaker is a way of creating new game sessions, of broadcasting those sessions to any interested clients, and allowing clients to join game sessions. So all of that Sphere 1 functionality, or almost all of that Sphere 1 functionality, is taken care of by your matchmaker. A client, one of the clients, will decide to host a game. It'll ping the matchmaker to create a game. The matchmaker will then broadcast that game to all the other clients. The clients can then choose to join that game, and then everyone is connected. Once everyone is connected, the relay server takes care of routing that traffic between everyone who's playing. So you don't have to worry about any of that. All you need to worry about is ensuring that anyone who wants to host can get in touch with that matchmaker, and it takes care of the rest. It should be noted, however, that the Unity Multiplayer Services are not a dedicated server. None of your game logic will be running on these services. You still need to take care of all of your game rules processing, all of your lag compensation. Anything that has to do with your game logic still needs to take place on your clients. The Unity Multiplayer Services simply act as an intermediary. The second sphere of functionality is taken care of by our high and low level APIs. So once we've got our packets as given to us by the Unity Multiplayer Services, we need to process those. The high level APIs strip away a lot of the drudgery there. They break multiplayer down into a series of very useful components that you can attach to game objects that takes care of synchronization of objects, of distributing messages to objects, and even some of the behavior that you want. For instance, moving objects around is taken care of by some of these components. We'll go into that a little bit more in detail later, but the high-level API really allows you to implement multiplayer quickly and iterate quickly on those features without having to worry about the nitty-gritty of how to distribute your messages and how packets are broken up and deserialized. You don't need to worry about that at all. If, however, you do want to worry about that, the low-level APIs exist. These give you full access to the transport layer of Unity, which means you can poke around in packets, serialize them as you need, deserialize them as you need, send what information you need when you need it, take care of channel prioritization. Basically, anything you need for pinpoint control and optimization is available to you as well. So no fear, the high-level APIs have not necessarily stripped away all that control. They've simply made it more accessible so you don't have to worry about it if you don't need to. Tanks is primarily built on the high-level APIs. Low-level functionality wasn't necessary to implement any of our gameplay. So bear that in mind as I continue with this video. Now, let's see how we implement all of that in Tanks. First, we need to start game sessions and get people connected to each other. Here we are in our lobby scene, which comprises our main menu and contains our server browser, our match creation menu, and all of the UI that you need for that. And you can see that we have a fair number of controllers here, but we have one in particular that's of interest, and that is the Network Manager. Now, the Network Manager is the backbone of Tanks. It inherits from an existing Unity class, and it is responsible for interfacing with the matchmaking server and the relay server, and ensuring that we can create and connect and do all of the things necessary for game session management. Looking at it in our documentation, you'll see that it provides a lot of very useful functions. Everything from querying whether a client is connected, as well as messages. For instance, if a client is disconnected, it allows you to override that and implement handling for that. You can see there are a large number. What happens if a match is created? What happens if a connection is dropped? There are a large number of messages that help you pinpoint and handle pretty much every single eventuality that may occur during a multiplayer game. That is very useful and very powerful because it means you don't have to worry about writing your own error message, parsing, or anything like that. It's just there, out of the box. You'll see that for our Network Manager, we've inherited, as I said, from the existing Unity one, and simply overridden many of these events here. And there is all of our handling. So you can see for client errors, for client connection, for client disconnection, and so on and so forth, we have a large amount of handling and very specific logic that we can assign to those events. Very powerful and very accessible. In addition, we have all of our standard wrapped functionality, such as starting a game session. Here you can see our start matchmaking game method. Alongside state management for our menu system, it contains two commands that it inherits from the Network Manager. Firstly, when we start a matchmaking game, we first start the matchmaker. This is a native command which connects to the matchmaking server, and then we simply ask the matchmaker to create a match for us, passing it things such as the game name, the maximum number of players that we want, as well as a number of other parameters that we don't necessarily use in Tanks but may be useful to you, such as a password string in case you want to password protect your game, or even a ranking so that you can implement ranked matches in your multiplayer. All of that is supported out of the box. In addition, we pass through a callback so that when we receive a callback from the matchmaking server, we can handle it however. If we fail to create a match, we can handle that. Otherwise, we can move on with our logic. So creating a match, as you can see, is a matter of 2 commands. And that's how easy the high-level API makes this sort of thing. Likewise, joining a matchmaking game, we previously start the matchmaker on our client to connect to the matchmaking server, and then on top of all of our other state management logic, we simply ask the matchmaker to join a match along with a set of parameters that we get from the server browser. And that's it. That's all you need to connect your players. No further logic required for advertising, no further logic required for packet routing, none of that. Quick and easy. That gets everyone into one lobby and lets them play the game. I encourage you to download the project and take a look at this Network Manager implementation for yourself to see exactly what we've done and how we've done it. It'll give a good amount of insight into how the interface with the Unity services works. Now that we've got our players talking to each other over the network, we still need to implement game logic. Now, this is easier to show you if we're actually inside a game scene to give you a bit of context. So I'm going to load up one of our multiplayer maps. And this one you may recall from our first video. It's a desert map with a number of mines. Right. Now, I'm going to be using a couple of terms here constantly, and it's important that you understand what they mean. These terms are client and server. For our purposes, the server is the host of our game, and the server is where all of the game logic is processed. This is because a network game is a tenuous thing. In order for it to be fair, all of your clients need to see the same thing in order for them to react to it, so that they are all playing the same game. If every client is processing its own logic, latency can mean that that information doesn't necessarily reach the other clients. So you have events on different clients drifting. To fix this, we ensure that anything of note, anything of importance to our gameplay, only occurs on one of those devices, and that information is distributed to everyone else, so that everyone else is seeing the same thing and reacting to the same game state. That all happens on the server, and when we say that the server has authority, that's what we mean. A client, on the other hand, you could say subscribes to the server. It sends what information it has to, such as input information, that allows it to interact with the game. But for the most part, all it's doing is receiving game state information from the server, just enough that the client can reproduce what's happening on the server so that the player can react to it. Now, there is another important caveat to multiplayer games. Unity multiplayer is not a silver bullet. Adding high-level API components, like I'm about to show you, does not magically make a single-player game playable on a network. There is a fair amount of planning and engineering that needs to go into making your game playable across a network. And it very much depends on what kind of game you're trying to make. A turn-based strategy game, for example, where people can take as long as they like, it needs to send a minimal amount of information from one client to the next. I mean, just information of what the player did on their turn. It's not time dependent. Players don't need to know immediately what has happened. There you can get away with a fairly simple implementation. Nothing is critical, packets can be delayed, the game state doesn't need to necessarily update immediately. In fact, it could update all at once. And you will build your game accordingly. Tanks, on the other hand, is a real-time multiplayer arcade game. It needs to be built so that the game plays as smoothly as possible for all participants. We need to take into account latency tolerance. We need to take into account lag. We need to ensure that even if the network's a bit slow, what each player is seeing on their screen is as close as possible to what's happening on the server. So bear that in mind when looking through this code. We've done a fair number of things to minimize the effect of lag and latency. By the time you watch this, we will have a document out that goes in depth into how we implemented lag tolerance and made the game as smooth as possible for all players. But for now, let's just take a look at the components and basic structure of the items in our game so you can get an idea of what's available to you in the high-level API and more or less how it works and how to use it. We'll start with the core of the game, our tank. And the tank is implemented in the complete tank prefab. I'm going to drag an instance onto scene. Now, you will see that there is no model on this tank. That is to allow us to have multiple tank models. We have different tanks selectable with different stats, and it's easier to have all the core logic in a single prefab than it is to split it amongst multiple ones. It can become a nightmare for maintainability if you have, for instance, 6 tank types and you need to make a single change and you've got to go through 6 prefabs. Much easier to have all of your core logic in a single, more or less empty tank prefab and then instantiate the per tank models as you need them. It adds a lot of scalability and maintainability to our game. Let's take a look then at our complete tank, which has all of our core logic on it. You can see so far we have all the usual suspects. We have a transform, we have our rigid body component, we have a couple of audio sources to play sound effects, and now we get to our scripts. You'll notice that on top of all of our regular parameters, we have 2 extra ones, a network channel and a network send interval. These are because these are not standard mono behaviors. They are what are known as network behaviors. You'll find these all over tanks. They're special types of mono behavior that can synchronize over a network. We use them extensively for logic and for gameplay processing. Now we move on to the pure high-level API stuff. Here you can see we have a network identity component. This component tells the networking system that this object is to be synchronized across the network. That means any variables that we've specified to synchronize that change on this object are rippled across to its counterparts on all of our clients. This means that we don't have to worry about parsing packets and assigning data to the correct objects. By assigning a network identity, all of this happens automatically for us. Now, generally, the value of synchronized variables that is distributed to all the clients is the value that's on the server. But you'll also note that we have this checkbox over here, local player authority. I made a big deal about server authority earlier, so why do we have this? Well, for certain components, we actually do want the client to have authority. Take this component, for example. This is a network transform. This is a built-in Unity networking component that allows us to synchronize the position and rotation of an object across the network. You can see that we have this linked to the rigid body on our complete tank prefab. That means that it'll take all of the values on that rigid body and it'll translate them across the network. Normally it's the server value that will be rippled out across, but because we have local player authority set in our network identity, the network will prioritize the value of the tank that is under the local player's control. It will take those rigid body values, it will send them to the server, and then the server will distribute them to all the other clients in the game. Why do we want to do that? One answer: latency. If we need to wait for a movement command to be intercepted by the server and then for our tank to move, then the game doesn't feel very reactive. It feels sluggish, and in fact, if the lag is too high, it'll feel as if the game is hanging. It'll be horrible to play. So by setting local player authority, we don't have to wait for the server to tell us where our tank is or in what direction it's facing. It happens instantly, and it feels good and reactive and snappy. You can also see here that the network transform allows us to limit what rotation information gets sent across the network. A good rule of thumb is to minimize the amount of traffic between your server and your clients, because if your game has to wait for a whole bunch of information, it's not going to react quickly, which is especially important in a fast-paced action game like Tanks. You don't want to waste transmission time and packets on information you don't actually need. Tanks is a 2.5D game. It only takes place on a two-dimensional plane, which means the only axis we need to care about is the Y rotation axis, and you can see that's what we've set here. We've also set it to sync angular velocity, which means that any forces applied to the rigid body, such as explosion blowback, are also transferred across the network. Now, a tank is a rather complex thing to explain in a short video. So let's, rather in terms of network behavior implementation, look at one of our mines here. Mines, you will note, have a network identity because they need to be synchronized across the network. That way, this mine will be treated as the same mine for the purposes of game logic between server and clients alike. All right. You'll note that we don't have a network transform attached to this object. That is because we don't need to worry about its positioning across the network. Its position is set on start, it is part of the scene, it's not going to move anywhere during the course of the game, so there's no need to synchronize direction or position. What we do have, however, is a network behavior here, our mine controller, and we're going to go into that. Now, behold, our mine controller script. You'll see that we've required a component of network identity here to ensure that the mine is treated the same across all instances of the game. And you'll see that mine controller inherits from level hazard. Level hazard, in turn, inherits from network behavior, which is what I was talking about earlier. The network behavior, as I've mentioned, is an expanded mono behavior that allows cross-network functionality. We'll see some of that functionality shortly. Let's go back to our mine controller. Now, you'll see that for the most part, it doesn't look too dissimilar to a regular single-player mono behavior, but we do have some differences. For one, you'll notice these tags, server callback and client RPC. Now, what these do is they specify certain methods as only being run on the server, in this case. In other words, only the server, the host of the game, will ever be processing these messages. And you'll see that these tend to involve game logic related things. We also have client RPCs. RPC stands for Remote Procedure Call, and they are very useful because what this allows us to do is it allows us to trigger these methods on clients from our server. This is very useful for synchronization, especially for these mines where all of our explosion logic and all of our gameplay logic is taking place exclusively on the server. Let's see how this works. You could see our standard on trigger enter message here. It's the same as in single player. This will be triggered once a suitable collider or an accepted collider enters this trigger, along with some other code which sets the internal state of this mine to, in this case, count down, because it's a time-delayed mine, you'll see that we also fire off an RPC to our clients to set triggered effects. So, to reiterate, what we're doing here is on the trigger being entered, we are initializing a countdown on the server and sending a message to our clients. What does this message do? Well, we're going to remotely tell it to set triggered effects on the mine across all clients. And all that does on the client is it changes the color of the mine light to a nice bright warning red, and also sets a sound effect going, in this case a warning beep, a proximity beep. Going back to the server, we can see that in our update loop, if the trigger time has expired, we call the explode mine method. Explode mine is once again only called on the server because it's game logic. That takes care of a number of things, namely resetting states, disabling our collider so that the mine can't be fired again, and also calling our explosion manager to create an explosion and deal damage to the tank. The explosion manager is one of the lag mitigating systems that we implemented that you will see better explained in the supplementary materials. All you need to know is that it deals damage and spawns explosion effects and then ripples them through to the clients as a standalone system. All we're doing here is we're asking the mine to spawn an explosion through this manager. And that will take care of all of the damage dealing and special effects. With that done, we call one final RPC to explode the mine. Now, because our explosion effect is being handled by our explosion manager, all we need to do on the clients is make the mine invisible. We don't need to worry about deactivating colliders and triggers and all of that because the client doesn't need to care about these things. All we need to do is hide our mine mesh and stop our sound. And that's it. Very limited functionality on our clients. It's just a matter of communicating the game state to our clients. Any of the meat, any of the actual game logic, anything that affects the gameplay is exclusively taken care of on the server. That concludes our second video. What I've shown you is a very narrow subset of all the functionality that's available to you via the high-level API. But even this small taste should show you how simple it makes synchronizing things over a network. As I said earlier, that doesn't mean that you don't need to put a little bit of thought into how your game is structured and synchronized. But it does mean that you can get to the business of putting your multiplayer prototype together and iterating without having to worry about any of the boilerplate functionality that Unity multiplayer services provide. For some of you, my brief taster won't be enough, so don't forget that you can download the whole Tanks project for yourself from the Unity Asset Store via the link in the description below and poke around in the code. Included in that asset package is a supplementary document that explains setup as well as explanations of some of the in-depth systems that we've implemented, specifically for lag mitigation. So go ahead and download that and take a look. As luck would have it, that's exactly what video 3 is about. In the next video, we'll be looking at how to download the project, how to set it up, and what sorts of things are available for you to play with and tweak in order to get a better idea of how everything works. Until then, thank you very much for watching. I'll see you again next time.